All right, welcome to Math 383 Complex Analysis. So this is going to be a slightly fun lecture for me. I recently just saw the professor, or one of the professors, Island Complex Form Analysis at a conference. So he would be, in some sense, your complex analysis grandfather. I will share some great stories of him after we have a video malfunction, either later today or some other time. All right, so what are we going to do today? So today, we're going to be talking about fractional linear transformations and Mobius transformations. Anything that's extremely important often has multiple names. I want to really emphasize the geometric intuition. So I'm going to cut back a little bit on some of the more standard algebraic proofs that are in the book and just highlight the key ideas and instead talk a little bit more about the intuition behind some of these results. I'm going to do the material in a little bit different order and just try to emphasize what does it mean to look at these. Now, again, because we are plotting complex valued functions of a complex input, this is 4 dimensions, so we have to play some games to try to make the plots doable in the confines we have. So we'll talk a lot about the automorphisms of the unit disks. These are maps from the unit disk to itself that will be one-to-one and onto, and just what can they look like. And the idea is to completely classify all automorphisms on the unit disk. And this is one of the big standard problems mathematicians always look at. You give us a set of objects. First, we try to show it's non-empty. Then we try to talk about maybe how many elements it has. And then we try to come up with, is there a rule that describes what are the possible elements? And what's wonderful when we get results later in the semester, such as the Riemann mapping theorem, we'll see that if we completely understand the automorphisms of the unit disk, we understand the automorphisms on anything that's conformally equivalent. So it's enough to just study one special case. We will constantly use the W log. What is the W log? Without loss of generality. So we always standardize things to make things a little bit easier. Without loss of generality, 0 is mapped to 0. Okay. And then as time permits at the end, I want to talk about something that's not in the book. Again, differences between real and complex analysis. So this actually involves one of my favorite moments of teaching at Williams, where I actually published a paper in complex analysis related to the Schwarz lemma from one of my complex analysis students. And so what I'll do is I'll talk a little bit about that paper, and I will give you the link to it, but I strongly urge you not to read the paper and try to see what you can do on your own first. Right. So I went to Wikipedia to just look up fractional linear transformations. I learned them as fractional linear. They have it as linear fractional. Doesn't really make much of a difference. Essentially, these are matrices. These are maps of the form A, Z plus B over CZ plus D. So you give me a complex number Z, and you give me a quadruple A, B, C, D, and I can associate a new number to each input. What are the only values of Z where you are worried about this map? Yes. Yeah, minus D over C. At minus D over C, it blows up, but as long as we stay away from minus D over C, this is a well-behaved map. And Wikipedia talks about a lot of other places where you can generalize this. What are the possible values of A, B, C, D? Where do they live? We often have them live in integers. Sometimes we have them live in real numbers. Sometimes they say you can actually have them be matrices and look at matrix maps like this. Now, of course, if they're matrices, you have to interpret, well, what does it mean to divide a matrix by a matrix? So what might you mean by that? Any thoughts? Yes. Maybe multiply by the inverse, but then which way? And so as soon as you start dealing with matrices, things become far more interesting. Now, one thing, well, I'll talk about that in a moment. I'm not going to really do much about this, but there are certain things you should see before you leave the undergraduate realm. One of them is the Baker-Campbell-Hausdorff formula. It's the matrix version of e to the x times e to the y. So if e to the x times e to the y equals e to the z, what is z? And so z is actually given in an expansion involving the commutator. And so the commutator of x and y is just xy minus yx. So it's a measure of the deviation from commutativity. So if x and y commute, then the commutator is 0, and you'll notice that everything will just immediately collapse to z equals x plus y, which is exactly what you would get in the one-dimensional setting. This is very valuable. I heard some talk about differential equations a moment ago before class. If you're trying to solve differential equations, you can often write things down in terms of a matrix, e to the at. And then you might need to know, well, how do two matrices, if they're exponentiated, how do you combine them? If things commute, very easily. If things don't commute, it is hard, but it's worth knowing at least that there is a formula. Okay. So let me just add one slide to just talk a little bit about okay, matrix form of fractional intrinsic. So if I give you the map F, I'll call it A, B, C, D of Z is equal to AZ plus B over CZ plus D. You know, think about the matrix A, B, C, D. Now, if I'm giving you a map, I can often specify the map many different ways. Can somebody give me a map that would have the same effect as this map A, Z plus B over CZ plus D? Give me different values of A, B, C, D that will return the same output. Divide all of them by 2. So really, we can rescale A, B, C, D by any non-zero number. So without loss of generality, the determinant of A, B, C, D, which is AD minus BC, is what? So 1. Is there anything else we have to worry about? 1 or 0. Because if the determinant is 0, then if I rescale it, it's still going to be 0. So without loss of generality, it might be convenient to consider matrices where the determinant is equal to 1. Yes. So it depends what you're allowed to rescale by. So if I'm allowed to rescale by complex numbers, I could actually rescale everything by I, and then that would change the determinant by -1. So again, it's a function of where you're allowed to behave. So if I give you F of A, B, C, D of F of alpha, beta, actually no, let's use capitals, of A, B, C, D of Z, what do you think is true about this? So what would you conjecture? Yes. So you think that order doesn't matter? So since I'm talking about matrices, so that's a great thing to check. And so let's see what we can do today. And so what I want to do now is I want to share screen. So let's go F of C, A, B, C, D. It's going to be AC plus B over CZ plus D. And then let's look at F of Z, A, B, C, D. A, B. I can't do that. Why can't I do that? Because D stands for derivative in Mathematica. So if I try to use it like that, it won't work. So I'll do E, F, G, H. I've already defined F. Yeah, we knew that one. A1, B1, C1, D1, A2, B2, C2. Okay. Now I can put in a simplify and see if we can make it look a little bit nicer. And now what I can do is I can do it the other way. So see if it makes a difference on the order. Do those look the same? pretty sure they're not the same. One way you can be pretty sure is I can just take this and I can subtract. And then I'll put a simplify around all this. And so it's possible that this is really 0. So how can we check to see if it's really 0? Yes? Try random value, right? Let's put z equals, 1/2. And now, looking at this, I've got a negative A1, A2. So there's a lot of similarities, but it doesn't look like they are identical. And so I should be able to take a special case, send one of the b's to infinity and whatnot, and see that they're not the same. So, but again, this is the power of being able to quickly do some calculations like this. Does the order matter? All right, for the next thing is, let's go back and let's look at f of f. We check 2 different things. What does this look like over here? I cannot write here, unfortunately. So what I'll do is I'll take a screenshot. Excellent conjecture. Oh, I think I went to the screen. When I look at this, over here, this looks like an FLT, right? It looks like it's A1, A2 plus B2, C1 of Z plus A2, B1 plus B2, D1 divided by, and then down below, it's going to be A1, C2 plus C1, D2, Z plus B1, C2 plus D1, D2. So hopefully I've written things correctly. So the question is this just equal to f of, say, alpha, beta, gamma, delta of Z? And if so, what alpha, beta, gamma, delta do you think it might be? So a great conjecture is multiply the matrices. So if we have F1, let's let gamma be A, B, C, D, or maybe gamma K is AK, BK, CK, DK. And so F gamma K of Z is AKZ plus BK over CKZ plus DK. So the conjecture is F of gamma 1 of F of gamma 2 of Z is equal to F of, say, gamma of Z, where gamma is what? So I believe that's the right order. If not, try gamma 2, gamma 1. And so you now have a conjecture to prove. Is this a hard conjecture to prove? How could you do it? Right. And what's that called? Proof by? There's a special phrase that people use for just doing it out. Brute force, right? unenlightening. This is where you can be a little bit of a snob. You can say, okay, yes, you've proven the result, but this is not an elegant proof. And I despise brute force proofs, because it gives me no intuition as to why it's true. I have the result. I'm grateful for the result. I'm glad I can use it. But at the end of the day, why is it true? So the question is there another way to prove this, a way that's more elegant? What you could do is try a sequence of special matrices. So how many people have taken linear algebra? This is basically just who's awake right now. We waive some requirements for classes, but linear algebra is not one of the ones that we waive. Okay, so in linear algebra, did you ever look at sequences of elementary matrices to move a matrix from one form to another? If you're very lucky and you have a unified multivariable calculus linear algebra class, you can actually use this in discussing things like the change of variable formula, and you write a more complicated transformation in terms of a string of easier ones. And the idea here is maybe we prove it for special matrices and then show that any matrix can be written as a product of these special matrices. So try to do it that way. So I'll make that extra credit. And the extra credit, just to be clear, is not the brute force calculation. I have no desire to read that. I think I've shared with you my story on Morley's theorem. Did I not share my story on Morley's theorem? I actually have this in my office. I can bring it down. So if you take any triangle and you trisect the angles, and by trisect, I mean just, theoretically, I don't actually have a trisector, sadly. And then for each, this is going to be terrible, but for each pair of trisectors that's closest to a side, connect them, and the picture's going to be horrible. Draw the resulting triangle. What kind of triangle do you get? Nope. And again, that's reasonable because my picture sucks. Equilateral. Yes. And so walking to the math department one day in grad school, one of my friends remarked about how it's sad that there's no simple proof of this. And I said, oh, it's really easy. You just write down the coordinates of the vertices, without loss of generality. This is 0, 0. This is 1, 0. This is XY. And then you write down the coordinates of the 3 points of intersection. You calculate the squares of the lengths, and you show that the squares of the lengths are equal. And so he bet me, not that I couldn't, but that I wouldn't have the patience to finish this before we graduated. So it took 1.5 years to eventually, finally write it down. I was allowed to use programs like Mathematica to expand things out. Every time lines intersect clear denominators, you end up getting polynomials in like degree 48 in the variables being like 1/3 of the tangent of the angles. That was the cleanest thing I could find. And so he owed me a dinner not to exceed $12.50. If I had failed, I would owe him ice cream not to exceed $2.50. I still bought him the ice cream for teaching me an extremely valuable lesson. Just because you can do something one way does not mean you should. It at least proves Morley's theorem. It's the longest proof, I think, of Morley's theorem in existence. There's some really bad journals, which I think would be very happy to publish this for a couple $100 per page, especially considering how many pages it is. John Conway has the best proof I've ever seen, where he starts off with an equilateral triangle and reverse engineers to get the original triangle. Absolutely brilliant 1- and 2-page proof. Strongly recommend if you want to see some nice mathematics. Look at almost anything he does. In particular, his proof of Morley's theorem is a great one. So for extra credit, if you want, do the non-brute force proof of just going through and showing. But again, what I love about being able to use something like Mathematica for symbolic calculation is you can start building intuition very quickly. Does it matter the order in which I apply the functions? It looks like it does. I can choose some special values, choose some special values of the A, B, C, Ds. It looks like I'm going to get a new fractional linear transformation. So I now have a conjecture as to what it should be. Okay. So we have already seen some examples And so we talked about, last time the map I minus z over I plus z, and then I 1 minus w over 1 plus w. These are the conformal maps between the upper half plane and the unit disk. Another one we could do is 1 plus z over 1 minus z, which takes the upper half of the disk and maps it to the upper right quadrant. So again, there's lots of maps like this that we can study that have lots of wonderful applications. All right. Matrix form of the FLT. So we've already really talked about this. I'll just choose some very special ones that I want to do. Let's say we take gamma to be 1, 1, 0, 1. Then what is f of gamma of z? That's going to be z plus 1 over 1, or just z plus 1. So this is translation. And another good one to take, and we often denote this matrix by T. Another good one to take is 0, negative 1, 1, 0. Then f of gamma of z is going to be negative 1 over z. And if z is in the upper half plane, so is negative 1 over z. And we often denote this map by S. And it turns out S and T generate SL2Z. So this is the set of all matrices A, B, C, D. A, B, C, D are in Z, and the determinant AD minus BC equals 1. So that's what this is the special linear. The special means determinant 1. So these are extremely useful matrices to look at. As a nice extra credit problem, I'll make this proof an extra credit. To be clear, when I give extra credits like this, that does not mean you're allowed to look it up online and then submit that. It has to be independent. Yes. So just go through and see what it would be. So it would be negative 1 over x plus iy multiplied by x minus iy over x minus iy. You would then get x squared plus y squared down below, and negative x plus iy up top. And so a lot of these is you roll up the sleeves, do the calculation. And when you do this, you see that it is going to be in the upper half plane. So these map the upper half plane to the upper half plane. And by generate, it means you can write it as a string of S's and T's. What do you think is the inverse of S? So what do you think undoes S? Yeah, S is its own inverse. So note S squared is the identity matrix. So when you're looking at your decomposition, you're never going to have an S squared. You're never going to have an S to the negative 1, because S to the negative 1 is the same as S. Okay. Question? Oh, right, yeah. So it equals I in quotes. And so what I will do, let me just add a blank page. So S is equal to 0, negative 1, 1, 0. What's S squared going to be? Negative 1, 0, 0, negative 1, right? But this is the same as negative 1 times the identity. And so what we really want to look at is P SL2 of Z, which is SL2Z, if you've seen some algebra, modded out by plus or minus the identity. Because really, when we're looking at the action, I and minus I, or gamma and minus gamma, have the same effect on Z. Because remember, when we're looking at AZ plus B over CZ plus D, this equals alpha AZ plus alpha B over alpha CZ plus alpha D. So I'm being a little bit lazy when I say S squared is the identity. It's not, but it's functionally the same as the identity. And so if I really look at your PSL2Z, I can be a little bit more, I can be careful and correct and accurate. Or I can be informal and just say, yeah, the negative identity is the same as the identity. This is one of the problems is often when you've worked in the field for a while, you get a little bit lazy and sloppy in what you say. And so please do call me on stuff like this. Okay, what I want to do now is talk a little bit about a very special map. So C of alpha, acting on Z is defined as alpha minus Z over 1 minus alpha bar Z, where alpha is any complex number with modulus strictly less than 1. So the question is this a good map? Well, it has some interesting properties. If I have it act on 0, it sends 0 to alpha. And if I have it act on alpha, it sends alpha to 0. So this is a map that switches 0 and alpha. We will show shortly that this actually maps the unit disk to the unit disk, and it's an automorphism. So this is a non-trivial automorphism of the unit disk. If I just asked you, can you give me an automorphism, a map that maps the unit disk to itself? You should be able to give me at least one without any trouble. Yes. F of Z equals Z, right? Yeah. Yeah. Okay, good. Can you tweak that a little bit and give me another one? It's very similar to F of Z equals Z. Negative Z. Okay, let's get a whole infinite family. E to the I theta times Z, as long as you put in any rotation, that's going to work. So the rotations are clearly going to be automorphisms of the unit disk to the unit disk, and they're going to fix the origin. What this map does is it flips alpha in the origin. So imagine I have a map that doesn't fix the origin, but it's an automorphism. Well, I can convert this to one that is now fixing the origin. And then, can anybody think of a map that fixes the origin and is an automorphism of the unit disk other than a rotation? Yes. Okay, so what word should I have said that I did not say? Holomorphic. So can anybody think of a holomorphic map? And another one you could do is you could actually be spreading things out. And you're given any point, you keep it along the same angle, but you move it so you decrease by a factor of 50% its distance to the boundary. So if you expand out like that, it will be a map from the unit disk to the unit disk, but it will not be holomorphic. So can anyone think of a can anyone think of a holomorphic automorphism of the unit disk that fixes the origin and is not a rotation? But it's no longer an automorphism. It's no longer one-to-one and onto. Yes.
Doing more of those rotating than doing that.
But we need to still fix the origin at the end.
When we do reflect.
It's not going to be holomorphic. And so let's just pretend we spend another 20 minutes and everything we tried failed. And so after a lot of effort, we might be led to believe that the only possibilities are going to be the reflections. And so that's one of the big goals we're trying to prove. So what I'm trying to do here is to show you what this map looks like. So again, we'll show in a few minutes that it does map the unit disk to the unit disk. What I'm doing here is I've defined a couple of functions, and I'm taking the real and the imaginary part of my function, alpha minus Z over 1 minus conjugate of alpha Z. And that way I can do a parametric plot. And what I'm doing is I'm plotting a circle centered at the origin of radius r, and I'm plotting it, and that's becoming this goldish circle over here, or this goldish shape. Is that a circle, yes or no? So how many people say it's a circle? How many people say it's not a circle? How many people are not sure? So I can change the value of r. I can make r smaller. Oh, no, I can't, because this is the static shell. So let me go back to Mathematica. And so if I go back to Mathematica, I can change the value of r, and I can make r smaller. Does that look like a circle? Is this a valid method of proof in a math department? No. So as R gets smaller, does it look closer and closer to being a circle? Let's see what happens as R gets larger and larger and larger. R is getting closer and closer to 1. Is this still looking like a circle? So do you think it's a circle? Or do you think that maybe this is kind of optical illusion going on? Yes. Ah, so you want me to remove the outer circle? You want me to remove it completely or just move it further away? I will completely remove it. So does that look like a circle now? And I can increase the value of R. Does that still look like a circle? Yeah, not a proof. I am putting the circle in here just so we can see where things are. And again, if you hit down here, you can see the actual values. I'm writing alpha as A plus BI. Without loss of generality, I might as well assume A and B on the upper in the first quadrant. And so it is interesting to see how you can potentially be misled. There's whole slews of visual illusions. And so I will leave this as a challenge problem. Is this a circle? So can you prove it is a circle? But it does give us a sense of trying to see what's going on. I can move where the center is. And you can see how moving the center changes things. And again, it's just good to be able to explore a little bit. Right. So again, here's the map. And we want to prove that it maps the unit disk to the unit disk. So to save a little bit of time, I have just pasted some of the calculations from the textbook. So the first is I'm applying the map to the points of the form e to the I theta. These are points on the boundary. And when you plug in those values and you just do a little basic algebra, you get e to the minus I theta w over w bar. So what can you tell me about the norm of such values? What does it equal? Oops. W here is just alpha minus e to the I theta. And because alpha has norms strictly less than 1, we know W is not equal to 0. So what can you tell me about the norm of C alpha? It's 1. So we know that C alpha maps the boundary of the unit disk to the boundary of the unit disk. Yes? Mm-hmm. No, alpha is fixed. For fixed alpha, I have a map. And what we just showed is if you take z to be of the form e to the I theta, if you take z to be on the boundary of the unit circle, then it maps the boundary of the unit circle to the boundary of the unit circle. So what must be true in the interior? So if the absolute value of z is less than 1, then what must be true about C alpha of z? Yes. It's also less than 1. Why? So this is the maximum modulus principle by maximum modulus principle. So the only place it would not be holomorphic is if the denominator is 0. Well, but I'm saying you've got a ratio of polynomials in Z. This is going to be holomorphic unless the denominator is 0. And so because alpha has values strictly less than 1 in absolute value, the only time the denominator vanishes, you would have to have z equal to 1 over alpha bar, which would be modulus greater than 1. So this function is actually holomorphic not just on the unit disk, but on a slight extension of the unit disk. You can expand it out a little bit, and it's still going to be holomorphic. Okay, so now we know that we have a function that is, strictly less than 1 in the interior. And so this shows that it maps the disk into the disk. So maps D into D. Do we know if it's 1-to-1? No. Do we know if it's onto? No. We just know that it maps the disk into the disk. Okay, that's step 1. And the next step is to prove that it's 1-to-1 and onto. And the nice calculation is to apply C alpha twice. And so again, this is just straightforward algebra. When you go through and do it, at the end of the day, you get back Z. So it's its own inverse. So now, use this to show 1-to-1 and onto. So for example, if we wanted to show it was onto, want Z such that, say, C alpha of Z equals W for a given W. What would you take for Z? Yeah. Wait, say it again. Take Z equals what? Z equals C of Z? Not C of Z. Take C alpha of W, and then C alpha of Z would be C alpha of W. And since C alpha composed with C alpha is the identity, that just gets you W. So this is how you can show that it would be onto. And I'll leave the exercise of showing that it's 1-to-1, for you to play with. But it's really nice to know that it's its own inverse. Okay. So now I want to quickly state the Schwarz lemma. This is going to do the heavy lifting in trying to prove the results about the automorphisms of the unit disk. So the Schwarz lemma says the following. So imagine you have a holomorphic map from the unit disk to the unit disk. And without loss of generality, let's normalize so that f of 0 is 0. This is not a big deal. And in fact, this is why I've spent the time, and I did this out of order, by first introducing these functions C alpha. These C alphas are automorphisms of the unit disk that move alpha to the origin. So if you have a function that's a map from the unit disk to the unit disk that doesn't send 0 to 0, well, we can always adjust it by composing it with one of the C alphas so that now it sends 0 to 0. So without loss of generality, when I'm looking at an automorphism of the disk, I can assume it sends 0 to 0. And the Schwarz lemma says 3 things are true. The first is f of Z is strictly less than equal to Z for all Z. If for some Z naught other than 0, we have f of Z naught has the same size as Z naught, then f is a rotation. And the last one is if the first derivative is less than equal to 1 in absolute value. So the first derivative is always less than equal to 1 in absolute value. And if it ever equals 1 in absolute value, then f is a rotation. So this is essentially giving us conditions to determine when our map is a rotation. All right. So the first one, f of Z less equal to Z for all Z and D. Is it possible that we could have an equality for all Z? Yeah, f of Z equals Z, or more generally, f of Z is either the I theta to Z. Any rotation can give us an equality. So the theorem does not state if we have an equality for all Z that it must be a rotation. So I'll leave that as an extra credit. Does the absolute value of f of Z equals Z imply it is a rotation? So we want to show that f of z is always strictly less than or equal to z for any z in the disk. Okay. Oh, whoops. Sorry. Yes, you're right. That's right, because that's right. This you're right. Sorry. I was showing you just one special spot, but you're absolutely correct. You all get extra credit. All right, let me now erase this. Okay, so now, how would we prove this? Well, it's nice that we've chosen things so that f of 0 is 0. So as f of 0 equals 0, and f is holomorphic, i.e. analytic, we have f of z equals 0 plus a1z plus a2z squared plus dot, 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 dot. Okay. We can study g of z equals f of z over z. And note the absolute value of g of z is equal to the absolute value of f of z over z, which is less than or equal to 1 over the absolute value of z. So why is it less than or equal to 1 over the absolute value of z? What do we know about f? Yeah. We know f of z is less than or equal to 1 as f maps the unit disk to the unit disk. So we know g of z is less than or equal to 1 over z. Okay. Now, what we do is the following. So here is our circle of radius 1. And what we do is we look at circles of radius r, and we keep expanding r. We keep pushing the radius up. And we look at what's going on circles of radius r. So on a circle of radius r, we have the absolute value of g of z, which is the absolute value of f of z divided by z, is less than or equal to 1 over z, which is less than or equal to 1 over r. So f of z in absolute value is less than or equal to the absolute value of z over r. Yes? Now, this is true for any r less, yes?
Why the final?
Well, I have f of z over z is less than or equal to 1 over r, so just multiply both sides by absolute value of z.
No. Why is longer f is less than 1?
Oh, the circle radius are. Oh, because I did things very quickly. So why is it less than or equal to 1 over r? It's the maximum modulus principle. So this is by the maximum modulus principle. The largest the function has to be an absolute value has to occur on the boundary. Therefore, I must have this happening when the absolute value of z equals r. And so now we know that the absolute value of z is less than or equal to the absolute value of z over r. But this is true for every value of r less than 1. So you take the limit as r goes to 1, and you get that the absolute value of z has to be less than or equal to z. If you're a little bit uncomfortable with this, imagine that there was some point where f of z was strictly larger in absolute value than z. Then you'd be able to find an r where this would no longer hold. So again, if you're not comfortable with this, go through and actually show, well, let's assume that it was larger at one point, and we'll get a problem with that. We'll get a contradiction. All right, for the second one, if for some z naught we have that the absolute value equals z naught, then f is a rotation. And so here's what the book wrote. For 2, we see that f of z over z attains its maximum in the interior of D, because we know that f is at most 1. We've looked at this function g of z, and it must therefore be constant. So this was the part I wanted to talk about. So why does the function have to be constant if it attains its maximum inside? Yes. Well, the maximum modulus says it attains its maximum on the boundary. Okay, but so why can't you attain your maximum in the interior as well? It is maximum modulus. Right, and so what I'm asking you is why? So it is in the theorem, but what is it that allows us to then? Good. And so the problem is, let's say this value of z naught has the maximum value. By the open mapping theorem, it maps into a small little open neighborhood about that, which means if I have the origin over here, if I go a little bit in this direction, I can find a point that's going to make the value a little bit larger. And so it is true, this is part of the maximum modulus principle, but we are really using the open mapping theorem to really make this explicit. That if you did attain your maximum in the interior, because the image is an open set, you would also have to obtain something a little bit larger as well. And so now the rest of the proof is standard. So we then get that f, since f is not constant, we get f of z. Oh, okay, right. So we get that f of z over z itself has to be constant. And if f of z over z is constant, let's call that constant c. The only possibility for c is it has to be 1 in absolute value. And so if c has to be 1 in absolute value, we can write it as e to the I theta, and therefore it's a rotation. And then the last one is that if equality holds, then f is a rotation. Given that we only have 2 minutes left, I'm not going to go through this right now. I'll leave this. We'll either finish it in class tomorrow, or I'll just leave it as an exercise. But again, it's viewing the function f of z over z. I wanted to just briefly mention the paper that I don't want you to read. I'm putting the links here. And actually, I'll probably delete that slide. So the question is, the Schwarz lemma is beautiful. It has a lot of nice statements. And let me just quickly copy this. So here is the Schwarz lemma. What if we have f from -1 to 1 to -1 to 1 is a real analytic function? Let's say it's an automorphism. What is true? And of course, we'll have f of 0 equals 0. What is true about the size of f prime at 0? So in the complex case, we have the result that the first derivative is bounded by 1. And at the origin. And if it actually equals 1, then it's a rotation. Is there something similar in the real case? How large can the first derivative be at the origin? Do you think it also is bounded by 1? Do you think it can be arbitrarily large? Do you think there's a new universal constant that describes how large it can be? And so, think about this. Do not read the paper. I'll make extra credit. What can you say? And the amount of extra credit will be related to how good of a bound you can get on f prime of 0. So if you show that you can't do better than f prime of 0 equals 1, then that will be full extra credit. Do you think you can get at least f prime of 0 equals 1? Yes, what function can you use? I'm sorry,
Z.
Z or X or negative X. Okay, so we know we can get at least F prime of 0 to be as large as 1. Can you get anything larger than 1? And if so, how much larger? So again, don't look at the paper. It's just there that, if you want to see it, it is there. But it was, a great moment in the class where, we actually investigated and saw how far you could go. All right. Have a great day.